following question reads that trihalomethanes are organic molecules in which three of the hydrogen atoms of methane are replaced by halogen atoms, for example, CHF3. The equation shows a reaction to produce CHF3. So there's a reaction that is given, and in that reaction CHF3, a trihalomethane is being produced, and you're given. You're then asked use the data to calculate the enthalpy change of the reaction for this formation of CHF3. So for this reaction, we need to find out the enthalpy of formation. And what is provided is the enthalpy of, we're provided with the enthalpy of formation of all the reactants and all the products. You would notice that there's CHI3, and you're given the CHI3 enthalpy of formation. You're given EGF's enthalpy of formation as well. You're given CHF3's enthalpy of formation as well, and you're also given EGI's enthalpy of formation as well. So if you know the enthalpy of formation of all your reactants and also your products, so these are all known, then the enthalpy of that particular reaction can be easily obtained by using the formula, which is that enthalpy of reaction is basically the sum of the enthalpy of formation of products minus the enthalpy of formation of reactants. So what I'm going to do is I'm going to sum up the enthalpies of formation of my products and subtract the enthalpy of formation of my reactants, and in that way I would be able to figure out the enthalpy of that particular reaction. So this is what we are going to do. So our enthalpy of reaction is going to be, my products are, look at the first product, which is CHF3, which is given as minus 6. So that's my first product. It's minus 6, 92.9. The other product is AGI, which is over here minus 61.8. So that is minus 61.8. And I need to multiply that by 3 because in the equation, in the products, there are 3 AGIs. So I would multiply that by 3. So this is my product, and I'm going to subtract my reactants, minus my reactants. So my reactants are CHI3, which is minus 182.1. So it's minus 182.1. And the other reactant is AGF, which is minus 204.6. And I'm going to multiply that by 3 again because they are 3 AGFs. So it's product minus these are my reactants. So it's going to be product, which is this enthalpy of formation of the products, minus the enthalpy of formation of my reactants. And the value that I'm going to get for this is going to be, so on my calculator, I'm getting this value, minus 82.4 kilojoules per mole. And so I'm going to write this over here. This is where the working should have been done, minus 82.4 kilojoules per mole. Now let's move to the next part of the question, which is that the graph shows the relationship between PV and P at a given temperature for CHF3 and an ideal gas. Now this is a very typical graph for PV versus pressure graph. So it's a PV versus pressure graph, and for an ideal gas, this PV is a constant because PV is equal to nRT. If number of moles of a gas are a constant, R is already a constant, it's the gas constant, T temperature is kept a constant, then pressure and volume, the product is going to be a constant, because if you increase pressure, volume would decrease. So if you increase pressure, volume would decrease for a gas, but the product would remain a constant. Vice versa, if you decrease pressure of a gas, volume increases, but the product pressure into volume would remain a constant. So for an ideal gas, PV is going to be a constant. So this is the dotted line that's drawn over here. But this is for an ideal gas. Real gases don't follow that trend. Real gases usually have this graph. Their PV is never a constant at any pressure. At lower pressures, it's usually lesser than the ideal gas PV, and at higher pressure, it generally deviates and is higher than the ideal gas PV. So let's look at the question now. The first part is that they've already said that CHF3 is not an ideal gas. State 3 basic assumptions that scientists make about the property of ideal gases. So I've written down the 3 basic assumptions, and the first one is that particles have negligible volume compared to the volume of the container. So gas particles, they occupy a negligible volume. What that basically means is that if I have a container that is filled with gas, then the gas particles themselves have negligible volume. Most of the volume that is being occupied is just empty spaces. So if there's a gas present in a container and that gas is occupying a particular volume V, then most of the volume is just empty space. The particles themselves have this tiny little particle is going to itself, it's going to have very little volume. So most of the volume that is being occupied by a gas is just empty spaces. That's the first assumption. The second assumption is that the intermolecular forces are negligible, so which means that gas particles are not going to attract each other very strongly, because if they attract each other very strongly, they would probably be in liquid or solid state. But since gases, the particles are not attracting each other very strongly, so they're far away and they're freely moving about. So they have negligible intermolecular forces, and the collisions are elastic, which means that when they bounce around, they don't lose energy or they gain energy. One would lose energy, the other one would gain energy, but there would be no net energy lost to the surroundings. So most of the collisions between gas particles are going to be elastic, or they're going to be approximately elastic. Now, moving to the next part of the question, you're now being asked to explain why CHF3 deviates from the property of an ideal gas at pressures greater than 300 atmospheres. So we need to prove why is CHF3 deviating over here. Greater than 300 atmospheres, this is the point. After this point at 300 atmospheres, the real gas starts to deviate a lot from the ideal gas. So why is that happening? The reason why it's happening is because we had a very basic ideal gas relationship, which was that PV is going to remain constant. If I keep on increasing pressure, the volume of a gas should ideally keep on decreasing. So, and this pretty much makes sense. Keep on increasing pressure, volume keeps on decreasing, but the product P into V would remain a constant. And that was true for an ideal gas. Let me quickly explain this relationship, which is that over here there is a gas and there is a movable piston. If I increase pressure, what that means is that if I increase pressure, the gas is going to compress and the volume would decrease. So what's going to happen is, so over here you can clearly see what's happening. You've increased pressure, the gas has compressed and the volume decreases. So higher pressure, volume decreases, product remains a constant. But this relationship holds true up to a certain point. After a point, a gas at a particular high pressure gas would be incompressible. What that means is, let me draw a diagram again. So here is this diagram over here, and you can see that at a very, very high pressure, if you have compressed a gas to a certain point, after that, all the gaps are gone and the gas would become incompressible. And at that point, beyond that point, what would happen is that you're going to keep on increasing pressure. You keep on increasing pressure no matter how much pressure you apply, how much force, downward force you apply. You keep on increasing pressure, but the volume is going to remain constant. Volume becomes constant. The gas is going to become incompressible beyond a certain point. So if you keep on increasing pressure and the volume has now become constant, that means that the product P into V is going to increase, because the pressure term is increasing and the volume term is not decreasing. The pressure is constantly increasing and the volume has become constant, which means pressure into volume, the product would keep on increasing. So you can look at the graph over here and you can notice that beyond this pressure, 300 atmosphere, the gas has become incompressible. So you keep on increasing pressure, but the volume would become constant and the product P into V would keep on increasing. So beyond a certain pressure, you keep on increasing pressure, the pressure into volume product would start to increase, because the pressure term increases, whereas the volume term actually becomes constant after a certain high pressure. So the answer that I'm going to write over here is that particles are so close together at high pressure that there are fewer gaps and gas becomes incompressible. They all join together, the gas is now incompressible. So if you increase pressure, volume would become constant, it would not change. So particle size becomes significant. Initially, for an ideal gas, it was insignificant, but now the particle size would be significant compared to the volume that the gas occupies. In part C of the question, you're given that different trihalomethanes reacts with O2 to produce carbonyl dichloride. And this is given over here. HCl is also released as a product of this reaction. Write an equation for this reaction of CHCl3 with O2. So this over here is the equation that I've written. It's CHCl3 half O2 reacting to produce carbonyl dichloride, which is this, and an HCl molecule. Now let's move to the next part of the question, which is related to NMR spectrum, infrared spectrum, which is that the conversion of CHCl3 to carbonyl dichloride can be monitored by infrared spectroscopy. The infrared spectrum of carbonyl dichloride is shown. So this is the infrared spectrum that is given, that is provided to us. And we are now being asked, on the infrared spectrum of carbonyl dichloride, identify within X the absorption that would not be present in an infrared spectrum of CHCl3. So this is the infrared spectrum of carbonyl dichloride. It's C double bond O, and two Cls would be attached. Now I've copied a piece of the data booklet, and there's this C double bond O absorption, infrared absorption in amides, ketones, aldehydes, carboxylic acid esters. These are the functional groups where this C double bond O bond is present, and this bond would vibrate and it would absorb the following frequencies. It would either absorb any of the frequencies around the solar 1600 to 1750 range, and it's going to be a strong absorption. So if you look at this molecule over here of carbonyl dichloride, you would notice that there is a C double bond O group present, and it's going to absorb a frequency somewhere in this range, which would be a strong absorption. So this absorption around the 1600 to 1700 range, this is the C double bond O absorption. This is the bond that is going to be absorbing this infrared spectrum somewhere around this range. So this absorption at wave number 1600 is going to be present in this molecule, whereas we were supposed to compare it with CHCl3. In CHCl3, there is no C double bond O present. So that is one difference that would be so that is one difference between the absorption spectrum of CHCl3 and the carbonyl dichloride that we had this spectrum for. So on the infrared spectrum of carbonyl dichloride, identify with the next absorption that would not be present in infrared spectrum of CHCl3. So I would mark it with an X over here. So this spectrum, this peak is not going to be present, and the reason is that there is no C double bond O in CHCl3. Let's move to the next part, which is part 3, and now we are being asked to suggest another difference between the infrared spectrum of CHCl3 and carbonyl dichlorides. We need to come up with another difference. So again, drawing carbonyl dichloride, and the other one is CHCl3. Now the other difference is going to be the CH bond. This CH bond is present in CHCl3, but it's not present in carbonyl dichloride, so it's absent over there. So this is going to be the other difference. So CH absorption, which generally occurs at somewhere around 2800 wave number to 3000. You can refer to the data booklet on this. This bond is going to be, this absorption is going to be present over here, but not in this molecule over here.